Imagine traveling from Beijing to Shanghai, a distance of over 1,300 kilometers in just 2 hours. No airports, no security lines, no turbulence, just a sleek, levitating train gliding silently above its track at speeds that rival commercial aircraft. This isn't science fiction. This is the reality China unveiled to the world in September 2022, and it left transportation engineers stunned, skeptics doubtful, and Western media outlets dismissive. For decades, the story of modern rail transport has been written by two nations: Japan, with its legendary Shinkansen bullet trains, and Germany, the birthplace of magnetic levitation technology. These countries have spent generations perfecting railway systems, accumulating patents, expertise, and global prestige. China, by contrast, entered this race late, decades behind, with limited indigenous technology and virtually no track record in advanced rail engineering. Yet today, something remarkable has happened. The student has become the master. The latecomer has leapfrogged the pioneers. And the technology that was once dismissed as a costly fantasy is now racing toward commercialization at breakneck speed. To understand where China stands today, we need to rewind to the beginning of this century. In the year 2000, China's railway network was antiquated, slow, and overcrowded. Diesel locomotives chugged along aging tracks at speeds barely exceeding 100 kilometers per hour. For a nation undergoing explosive economic growth, this infrastructure was a bottleneck, a brake on development that needed urgent attention. The solution? Look abroad, learn fast, adapt faster. China adopted a strategy that would become its hallmark: technology transfer through collaboration. The government invited foreign rail manufacturers, Siemens from Germany, Alstom from France, Kawasaki from Japan, to partner with Chinese companies. The deal was straightforward: access to China's massive market in exchange for sharing technical know-how. What followed was one of the most aggressive infrastructure build-outs in human history. Between 2008 and 2025, China constructed more than 45,000 kilometers of high-speed rail lines, more than the rest of the world combined. Cities that once required 12-hour train journeys were suddenly connected in under 3 hours. Regions that had been economically isolated were integrated into national supply chains overnight. But China didn't just copy, it innovated. Chinese engineers modified designs, improved efficiency, reduced costs, and localized production. Within a decade, China wasn't just building trains, it was exporting them. Chinese rail technology began appearing in Indonesia, Thailand, Turkey, and beyond. By 2020, China's high-speed rail network carried over 2.3 billion passengers annually. That's more than 3 times the entire population of Europe. The system had become the backbone of domestic travel, a symbol of national achievement and a source of immense pride. Yet even as China celebrated this success, its engineers were already looking beyond conventional rail. Because no matter how fast traditional high-speed trains become, they face a fundamental physical limitation: friction. Steel wheels on steel rails. At speeds above 400 kilometers per hour, the friction, noise, and energy consumption become prohibitively expensive. Maintenance costs skyrocket. Safety margins narrow. There's only so fast you can push a train that actually touches the ground. Unless, of course, you remove the ground from the equation entirely. Magnetic levitation, Maglev for short, isn't a new idea. The concept dates back to the early 20th century, but it wasn't until the 1960s that engineers began seriously exploring its potential for transportation. The principle is elegant. Use powerful electromagnets to lift a vehicle above a guideway, eliminating physical contact and therefore eliminating friction. 2 countries pioneered this technology. Germany developed the Trans-Rapid system, a high-speed maglev that used attractive magnetic forces to pull the train upward toward the track. Japan pursued a different approach with its SE maglev, using superconducting magnets and repulsive forces to push the train away from the guideway. Both systems worked, Japan's test train reached an astounding 603 kilometers per hour in 2015, a world record that still stands. Germany's Transrapid operated successfully on a test track in the 1980s and even ran commercially on a short stretch in Shanghai, a project inaugurated in 2004. But here's the problem. Neither system ever achieved widespread deployment. Why? Cost, complexity, compatibility. Building Maglev infrastructure requires completely new guideways. You can't simply upgrade existing rail lines. The electromagnetic systems demand precision engineering down to the millimeter. The power requirements are immense. And because Maglev trains can't run on conventional tracks, you need a dedicated network, which means massive upfront investment with no guarantee of return. Germany eventually shelved its Transrapid program after a fatal accident during testing in 2006 and mounting financial pressure. Japan continued development but struggled to justify the economics, especially given its already excellent conventional high-speed rail network. By 2014, Maglev technology had become something of a transportation curiosity. Technically impressive, but commercially impractical. A solution in search of a problem. That's when China made a decision that surprised many international observers. Rather than abandoning Maglev as Germany had, or moving cautiously like Japan, China would go all in. The Chinese government announced a 30 billion yuan investment, equivalent to roughly 4.3 billion US dollars, to develop a domestically designed high-speed Maglev system. The goal was audacious: create a train capable of reaching 620 kilometers per hour, roughly twice the speed of China's fastest conventional high-speed trains. Critics were swift and harsh. Western transportation analysts called it wasteful. Financial commentators questioned the economic logic. Some media outlets openly mocked the project, suggesting it was driven more by national prestige than practical need. China's Maglev fantasy, read one headline. Billions wasted on a train to nowhere, proclaimed another. But China pressed forward. The research and development process began in earnest in 2014. Teams of engineers, physicists, and materials scientists were assembled in cities across China: Beijing, Shanghai, Qingdao, and Chengdu. The mission was clear. Don't just replicate foreign technology. Develop something better. One of the first challenges was the propulsion system. Maglev trains use linear motors, essentially unwrapped versions of rotating electric motors, to generate thrust. Unlike conventional motors that spin wheels, linear motors create force directly along the direction of travel. This allows for smooth acceleration and incredible speeds, but it requires sophisticated electromagnetic control systems that must adjust thousands of times per second. Chinese engineers spent years perfecting these systems, testing different configurations of superconducting magnets, experimenting with various cooling methods, and developing control algorithms that could maintain stable levitation even at extreme velocities. Then there was the guideway itself. For a Maglev train to operate safely at 620 kilometers per hour, the track must be extraordinarily precise. We're talking about tolerances measured in single-digit millimeters over stretches spanning dozens of kilometers. Any deviation, any bump, any misalignment could destabilize the magnetic field and compromise safety. This demanded new construction techniques, new materials, and new quality control processes. Chinese engineers incorporated rare earth elements into the electromagnetic systems, utilized advanced concrete formulations for the guideway structure, and developed sensor networks capable of monitoring track conditions in real time. By 2019, 5 years into the project, China had reached a critical milestone. In the coastal city of Qingdao, home to one of China's leading rail manufacturers, the first prototype rolled out of the assembly facility. It wasn't just a test vehicle or a concept model. It was a fully functional, full-scale Maglev train designed for commercial operation. Initial tests were conducted on a short experimental track. Engineers monitored every parameter: levitation height, energy consumption, electromagnetic interference, passenger comfort. Adjustments were made, systems were refined, and gradually, the train's performance improved. Then, in 2022, China made its international debut. At the Berlin Transportation Technology Exhibition, held, notably, in the birthplace of the Transrapid, China showcased its high-speed Maglev system to the world. Videos showed the train gliding effortlessly above its track, accelerating smoothly to speeds exceeding 600 kilometers per hour, then decelerating with equal grace. The technical specifications were impressive. The train could carry up to 600 passengers. Its energy efficiency, despite the high speeds, was comparable to conventional high-speed rail due to the absence of rolling friction. And perhaps most remarkably, the ride quality was exceptionally smooth. Passengers would barely feel they were moving at such extraordinary velocity. For China, this was a moment of technological validation. For Western observers, reactions were mixed. The criticism came from multiple angles, and it's worth examining each argument carefully because, well, they reveal deeper questions about infrastructure investment, technological ambition, and economic rationality. Argument 1. The cost is unsustainable. Building a single kilometer of maglev track, according to industry estimates, costs approximately $70 million or more. That's roughly double the cost of conventional high-speed rail. For a country like China, which would need thousands of kilometers of track to create a meaningful network, we're talking about potential expenditures in the hundreds of billions of dollars. Where would this money come from? China's economy, while large, faces significant challenges: an aging population, mounting local government debt, slowing growth rates, and regional inequality. Is this really the best use of scarce capital? Argument 2. The existing network is sufficient. China already has the world's most extensive high-speed rail network. Trains running at 350 kilometers per hour connect all major cities. For most journeys, this is fast enough. The marginal benefit of cutting travel time by another hour or two, critics argue, doesn't justify the massive infrastructure overhaul required for maglev. Argument 3. Safety and reliability are unproven. While test tracks demonstrate what's technically possible, commercial operation at scale is an entirely different challenge. What happens when maglev trains need to operate in extreme weather? How do evacuation procedures work if a train breaks down while levitating? What about electromagnetic interference with nearby electronics? These aren't trivial concerns. Argument 4. It's about prestige, not practicality. Some Western commentators suggested that China's maglev program is less about transportation and more about making a statement, showing the world that China can master any technology, no matter how advanced. It's a trophy project, they argue, designed to generate headlines rather than genuine economic value. These criticisms aren't entirely without merit. Large infrastructure projects can indeed become vanity projects. Cost overruns are common, and the history of transportation is littered with technologies that worked brilliantly in theory but failed in practice. So are the skeptics right? Is China's maglev program an expensive mistake? To answer this question fairly, we need to look beyond the immediate costs and consider the broader strategic picture. Because China's motivation for developing maglev technology isn't just about moving people faster. It's about, positioning for the future of global transportation. Reason 1. Technological leadership drives economic power. In the 21st century, technological capability increasingly determines national influence. The countries that master emerging technologies, artificial intelligence, quantum computing, advanced materials, next-generation energy systems, will shape global standards, capture intellectual property value, and dominate export markets. Rail technology might seem traditional, but it's actually a convergence point for multiple cutting-edge fields: electromagnetic systems, materials science, advanced manufacturing, AI-driven control systems, and more. Developing Maglev expertise builds capabilities that extend far beyond trains. Moreover, if China can make Maglev commercially viable, it positions Chinese companies to export this technology globally. Imagine future high-speed rail projects in India, Africa, Southeast Asia, or the Middle East using Chinese Maglev systems. That's not just infrastructure sales. That's technological influence that lasts decades. Reason 2. China's geography demands speed. China is enormous, roughly the same size as the United States. Major economic centers are separated by vast distances. Beijing to Guangzhou is 2,300 kilometers. Shanghai to Urumqi is over 3,000 kilometers. For such distances, conventional trains remain time-consuming, even at 350 kilometers per hour. Air travel is an alternative, but it comes with downsides. Airports are typically located far from city centers, security procedures are time-consuming, delays are frequent, and aviation's carbon footprint is substantial. Maglev offers a compelling middle ground, nearly the speed of air travel with the convenience and reliability of rail. If a Maglev network could connect China's major cities with journey times under 3 hours, it could fundamentally reshape how the economy functions. Business meetings could happen across 1,000-kilometer distances without overnight stays. Labor markets could integrate across provincial boundaries. Supply chains could move faster and more reliably. Reason 3. Learning by doing. China's approach to technological development has consistently followed a pattern. Start by learning from others, then improve through practice, then eventually innovate independently. This happened with shipbuilding, telecommunications, solar panels, electric vehicles, and high-speed rail itself. The Maglev program fits this model perfectly, even if the first-generation system proves too expensive for widespread deployment. The expertise gained in electromagnetics, in precision manufacturing, in system integration will inform future iterations. Version 2.0 might be significantly cheaper. Version 3.0 might be revolutionary. Technology rarely achieves its potential on the first attempt. Progress requires iteration, and iteration requires commitment through early challenges. Reason 4. Environmental considerations. As climate concerns intensify globally, the carbon efficiency of transportation becomes increasingly important. Maglev trains, powered by electricity, can be integrated into renewable energy systems. Their energy efficiency per passenger kilometer, despite high speeds, compares favorably to aviation. If China is serious about its carbon neutrality pledges, and the scale of its renewable energy build-out suggests it is, then investing in low-carbon, high-speed transportation makes strategic sense. So where does China's Maglev program stand today, and what comes next? As of early 2025, the technology has been proven at the prototype level. Test operations have validated the core systems, but commercial deployment at scale, that's still in the planning stages. Several routes are under consideration. One proposed line would connect Shanghai and Hangzhou, a distance of about 170 kilometers. Another would link Guangzhou and Shenzhen, two of southern China's economic powerhouses. These shorter routes would serve as proving grounds, allowing engineers to refine the technology in real-world conditions before committing to longer, more expensive lines. The Chinese government hasn't announced a definitive timeline for commercial service, which suggests a more cautious approach than some critics had expected. This is actually encouraging. It indicates that decisions are being driven by technical readiness and economic viability rather than arbitrary political deadlines. Meanwhile, research continues. Engineers are exploring ways to reduce construction costs, perhaps through modular guideway designs or alternative magnetic materials. They're testing different operational scenarios, examining how Maglev can integrate with existing transportation networks. They're studying passenger behavior, safety protocols, and maintenance procedures. In parallel, China continues expanding its conventional high-speed rail network. The two systems aren't in competition, they're complementary. Conventional rail serves medium-distance routes economically. Maglev targets the longest, highest traffic corridors where speed premium justifies higher costs. Interestingly, China's Maglev ambitions extend beyond its own territory. The technology has attracted interest from several countries looking to modernize their transportation infrastructure. The United Arab Emirates has explored Maglev connections between major cities. Saudi Arabia, as part of its Vision 2030 economic diversification plan, has considered high-speed Maglev for key routes. Even in Europe, where skepticism about Chinese technology runs high, some regions have quietly examined whether Chinese Maglev could offer better value than expensive domestic alternatives. This international interest serves China's broader strategic goals. If Chinese Maglev systems gain acceptance in foreign markets, it creates dependencies on Chinese technology, Chinese standards, Chinese maintenance expertise. This is the same dynamic that made American technology standards dominant in the post-World War II era. Of course, geopolitical tensions complicate these prospects. Western governments increasingly scrutinize Chinese infrastructure investments, worried about security implications and strategic dependencies. The ease with which Chinese Maglev can expand internationally will depend as much on politics as on technology. Stepping back from the technical details, China's Maglev program exemplifies a broader philosophy about infrastructure investment that differs markedly from the approach dominant in many Western countries. In much of Europe and North America, infrastructure decisions are heavily constrained by short-term financial calculations. Projects must demonstrate clear return on investment within defined timeframes. Risk aversion is high. Incremental improvements are favored over ambitious leaps. China operates with a different calculus. Infrastructure is viewed as foundational to long-term economic development, even if immediate profitability is uncertain. The willingness to absorb initial losses, to experiment with emerging technologies, and to think in multi-decade timeframes allows for projects that would never survive Western cost-benefit analyses. This isn't to say China's approach is necessarily superior. It can certainly lead to waste, overcapacity, and misallocation of resources. But it does enable a different kind of technological ambition, one that sometimes produces breakthroughs that more conservative approaches would miss. The Maglev program embodies this philosophy. It's a calculated gamble. Invest billions now in technology that might not pay off for decades, but if it does, it positions the country at the forefront of next-generation transportation. So, was the West right to laugh at China's Maglev ambitions? Or will those laughs age poorly as the technology matures? History suggests that dismissing China's technological capabilities is usually a mistake. 30 years ago, Western experts doubted China could manufacture quality consumer goods. 20 years ago, they questioned whether China could innovate rather than imitate. 10 years ago, they assumed China would remain dependent on foreign technology for advanced industries. Each assumption proved wrong. Not because China never failed or wasted resources, it certainly has, but because the scale of investment, the speed of learning, and the willingness to persist through setbacks eventually overcome initial disadvantages. The Maglev train, currently capable of 620 kilometers per hour, might never become commercially ubiquitous. The economics might not work. The technology might be superseded by something better. That's possible. But it's also possible that 20 years from now, travelers will board sleek Maglev trains in Beijing and arrive in Shanghai in under 2 hours, wondering how anyone ever thought such technology was impractical. It's possible that Chinese Maglev systems will operate in dozens of countries, setting global standards for high-speed ground transportation. It's possible that the skeptics of 2022 will look as short-sighted as those who dismissed China's high-speed rail plans in 2000. The only certainty is this: while critics debate whether it can be done, Chinese engineers are busy doing it. While analysts calculate why it won't work, Chinese manufacturers are building the components. While Western media dismisses the project as fantasy, Chinese scientists are solving the technical challenges one by one. Perhaps that's the real story here. Not whether any single technology succeeds or fails, but the broader narrative of a country willing to invest in ambitious visions of the future, even when conventional wisdom says it's impossible. Because ultimately, the impossible only remains impossible until someone makes it real. And if there's one thing China has demonstrated over the past few decades, it's that the boundary between impossible and inevitable is often just a matter of determination, resources, and time. The Maglev train glides forward, levitating above its track, defying both gravity and expectations. Whether it represents the future of transportation or an expensive detour on the path to progress, only time will tell. But one thing is certain. The journey has already begun, and the world is watching.